Okay, so first of all, I'd like to thank the organizers of this event. That's a pleasure to be here. That's the last talk, so I'll be as concise as possible. So I'll try to make it short. I'm going to talk about the enumeration of so-called Grothendieck dessins d'enfants. This problem is similar to that of Hurwitz. But let me start with a brief reminder. Just consider a two-sphere, mark some points on it, say m points, and consider the following counting problem. Compute the number of ramified covers of the sphere with a prescribed ramification profiles over the marked points. A ramification profile is a partition of the degree of the covering that is just the set of ramification orders of critical points, so preimages of these marked points. Well, this problem is too complicated to be accessible at the moment, so there are ways to consider some special cases of it. One of the cases is the so-called Hurwitz problem, is the following. You fix an arbitrary profile over infinity, say d1 to dn. dn is the number of preimages of infinity, and di's are the corresponding ramification orders at the points of the preimage. And over all other points, the ramification is simple. That means that these are just double points, and the corresponding profiles are 1 to the d minus 2 and 2. So there is, in each preimage, there is 1 point of order 2 and d minus 2 regular points. So in this setting, this problem is much simpler. And the numbers that count such coverings, they are called Hurwitz numbers. They're usually denoted by Hg, where G stands for the genus of the covering. And it depends also on the profile at infinity, d1 to dn. These numbers can be counted recursively. On this workshop, both Dima Zvonkin and Maxim Kazaryan told how these numbers can be computed. So let me remind you the main points. These numbers can be packed into a generating function that was denoted by h, and it depends on a parameter beta and the infinite number of variables p1, p2, and so on. So I'm trying to stick to the notation of Maxim Kazaryan here. And by definition, this generating series is the sum over all n, 1 over n factorial, sum over g, and all possible sets of non-negative numbers di. And here we have the Hurwitz number hg d1 to dn times beta to the m over m factorial p d1 up to p dn. And here well, m is the number of simple critical values, and this m is related to the genus by the Riemann-Hurwitz formula. So let me write it down. That's m is equal to 2g minus 2 plus n plus the degree. And the degree is just the sum of di's. So that's the generating function, and this generating function, as we heard lately, enjoys many interesting properties. So let me list some of these properties. The first property is that the exponential of h obeys an evolution equation of the following form. It's del e to the h over del beta is equal to w naught e to the h. This operator, w naught, is called the cut and join operator. And what is nice about this equation, that together with the initial condition, which is quite simple, at beta equal to 0, h is just p1. So this evolution equation and the initial condition determine the generating series h uniquely. So this also allows to write an explicit formula for the exponential of h for the partition function, and this equation looks like follows. That's e to the h is equal to e to the beta times w naught, the cut and join operator, times the exponential of the initial condition, e to the p1. From here, it immediately follows that this function h is a solution to the Kp hierarchy. That's the second property. H is a solution to the Kp hierarchy. So the equations of this hierarchy were written by Maxim Kazaryan in his talk. So I'll write a couple of equations somewhat later, but just in a few words, that's an infinite system of nonlinear partial differential equations, rather complicated, and generally speaking, it's pretty hard to decide whether a function satisfies this infinite set of equations. But here it's almost automatic because the operator w naught belongs to the Lie algebra of the Lie group that acts transitively on the space of solutions of KP hierarchy. That's the so-called GL hat infinity. And, well, this flow just moves along the Sato-Grassmannian. That's the space of solutions to the KP. So the evolution equation keeps us inside the Grassmannian. So we have a solution of the KP provided the initial condition is a solution. But here it's obvious all equations of the KP hierarchy contain derivatives of order at least 2, so linear functions are automatically solutions. So since P1 is linear, we have a solution of the KP hierarchy that depends on beta as a parameter. So we have a one parameter family of solutions or tau functions. The third property is really very special. That's the so-called ELSV theorem that was mentioned both by Dima and Maxim several times. This theorem claims that the Hurwitz numbers h small g di can be expressed in terms of certain intersection numbers on modular spaces of curves that are called Hodge integrals. And that's very special for this enumerative problem. And from that fact that there is an interpretation of Hurwitz numbers in terms of Hodge integrals, one can deduce that well, a proper potential built from these numbers obeys the topological recursion. So we also heard a lot about that. That's what one can tell very briefly about the Hurwitz problem and Hurwitz numbers. So I'm going to talk about a similar but somewhat different enumerative problem. Namely, I'm going to consider arbitrary ramifications, but I'm going to keep the number of critical values as small as possible. The smallest non-trivial number of critical values is 3. For 2 critical values, the problem is obvious. And 3 critical values give a non-trivial, first non-trivial example. So, what is so special about the ramified coverings with 3 critical values? That they play a special role because of the famous Bailey result. So let me formulate Bailey's theorem that claims that ramified coverings of the sphere with 3 critical values are really very special. This theorem says the following. Let C be a compact, complex algebraic curve. This curve is defined over the field of algebraic numbers over Q bar. Roughly speaking, you get the field Q bar by adding all roots of all polynomials with rational coefficients. So this curve is defined over Q bar if and only if there exists a meromorphic function or a covering of the complex projective line CP1 ramified over only over 0, 1, and infinity. So this theorem came like out of the blue. Its proof was, one way it was essentially known, and the other way it was so simple that nobody could really understand why this theorem wasn't known much earlier. But anyway, that's a famous result that distinguishes coverings with 3 critical values among all other coverings. My goal is to enumerate such coverings to some extent, and what I'll get is the analogs of the first property and the second property. So I'll show how to get an evolution equation for the generating function of the coverings with 3 critical values, and I'll show that this generating function is a solution to the KP hierarchy. What concerns the third and the fourth point, that's an open question. One can hardly expect something similar to ELSV here, because the dimension of the target space of the branch morphism is 0. The modulo space M03 is just a point, so there is not much space to write intersection numbers on the space. But there may be some other interesting algebraic interpretations of these numbers, but I'm not aware of any of them. And the same concerns the topological recursion. So since there is no clear relationship with intersection theory on modulo spaces, well, it's hard to guess about whether topological recursion for these numbers could exist or not. But anyway, so let's consider with let's continue with the coverings with 3 critical values, and it was Grothendieck who noticed that such coverings are described by pretty simple combinatorial objects that he called dessins d'enfants, or child drawings. Let me define what a Grothendieck's dessin is. Let us start with a Belli pair. A Belli pair is a pair that consists of a curve and a meromorphic function with 3 critical values. Then Grothendieck's dessin is the inverse image, F inverse, of the line segment, of the real line segment from 0 to 1. So this line segment belongs to the projective line. We take the inverse image of this line segment. That's an embedded graph in C. It's Bcolored. Its vertices are colored in two colors, either 0 or 1. It has a natural ribbon graph structure because, well, it's embedded. And that's a simple observation by Grothendieck that the isomorphism classes of pairs of Belli pairs are in one-to-one correspondence with isomorphism classes of dessins. So it was observed by Grothendieck soon after the Belli paper appeared. And it says that there is a one-to-one correspondence between Belli pairs and dessins. So to count the number of coverings is the same problem as to count the number of dessins or ribbon graphs with vertices colored in two colors. What is so interesting about Grothendieck's observation? From his observation, it follows that the absolute Galois group naturally acts on the space of combinatorial objects. The absolute Galois group is one of the most mysterious objects in mathematics, and very little is known about its structure in general. So Belli theorem, and together with Grothendieck's observation, they give her a way to study it through its action on dessins. Since dessins are rather simple, there was a hope that one could learn something new about the Galois group. But, it still wasn't quite so. There were quite a number of papers on this subject, but no really breakthrough in that direction. So the Galois group remains as mysterious, almost as mysterious as it was. However, it acts faithfully on dessins. And even in a relatively small subset of dessins, it acts faithfully even on trees. Okay, so I'm going to consider an object that is dual to dessin. First, let me notice that a design can be extended to a Bcolored triangulation of the surface. So if this is a complex plane or complex projective curve, that's the segment from 0 to 1. The real line divides the complex projective line into two triangles with vertices at 0, 1, and infinity. So the upper triangle is, say, let's call it white, and the lower triangle is black. And we can take the inverse images of these triangles. On C, they remain to be triangles, and we get a triangulation of a curve into triangles of two colors, black and white, such that triangles of the same color cannot have a common side. And we can take a dual graph to that triangulation. That's a three-valent graph. So let me write it. Let me draw it on the complex plane. And this graph has an additional feature that it's three-edge colored. Its edges can be colored in three colors. Say the edges that intersect the preimages of the ray from 1 to infinity we color in green. The edges that, well, okay, connect, that intersect the preimages of the line segment from 0 to 1 we color in red. And the edges that intersect the preimages of the ray from minus infinity to 0 in brown. So there is one-to-one correspondence between dessins and bicolored three-edge colored graphs. Even ribbon graphs. The ribbon graph structure is inherited from this picture at the preimages of white vertices. At white vertices, the order of half edges is green, brown, red, and the order of half edges at the preimages of black vertices is, so here it's green, brown, red, and here it's the opposite. It's green, red, brown. So to count the dessins, it's the same as to count Bcolored, three-edge colored ribbon graphs with such a ribbon structure. So now let me formulate the counting problem explicitly, more explicitly. So we are going to count the numbers. So let's see F be a Belli pair, and let gamma be the corresponding three-valent graph. Let's call it Belli graph. And let's denote by K the number of preimages of 0, by L the number of preimages of 1, and by M dash the vector M1 to M2 and so on, that describes the profile over infinity. In other words, the profile over infinity is 1 to M1. So there are M1 simple poles, M2 poles of order 2, and so on. And the total number of poles we denote by M. So, and we also put M to be number of preimages of infinity. So these numbers, they satisfy certain simple relations. Let me write them down. M is, well, let me start with, yeah, okay. M is just the sum of mi's. That's obvious. The degree of F is the sum of I times mi. And the genus is given by the Riemann-Hurwitz formula. It's namely 2g minus 2 is d minus the sum of k plus l plus m, the number of preimages of critical values. And let's call the set consisting of two numbers and the vector m the type of the Belli graph gamma. Now we are going to count the graphs of a given type. The corresponding number we denote by n with subscripts k and l of m dash. And by definition, this is the weighted sum or the weighted count of graphs of type K, L, M bar. The graphs are counted with weights that are the orders of the corresponding automorphism groups. So we have such numbers, and we can form a generating function. By definition, the generating function depends on the parameters S, U, V, P1, P2, and so on. And that is the sum over K and L from 1 to infinity. the sum over all vectors m bar with non-negative entries, nkl of m bar s to the d, the degree of the map, u to the k, v to the l, p1 to m1, p2 to m2, and so on. So that's the generating function, and the statement about this generating function is the following. Let us define two operators already considered by Maxim Kazaryan in his talk. L1 is the Virasor operator. It's the sum over I from 2 to infinity, I minus 1 pi del over del p I minus 1, and W1, that is the sum over I from 2 to infinity, the sum over j from 1 to I minus 1, I minus 1 pi pj del over del p j minus I minus 1 plus j I minus j p I plus 1 d squared over del pj del p I minus j. So that's this operator looks almost like cut and join operator. If there were no ones, minus ones, then it will coincide with cut and join, but cut and join operator has degree 0, and this operator increases the degree by 1, as well as this operator.
So is it I plus j minus 1 maybe in the first derivation?
No, that's just I stands for the sum of I and j in the standard notation.
There are pi and pj, or is it?
Yes, you're right. Thank you. Yeah, pj and pi minus j. Yeah, thank you. Okay, so and the statement is the following. There is the evolution equation for the exponential of f. Of the following form. It's u plus v times L1 plus W1 applied to the exponential of f. The second statement is that together with the initial condition, that looks like this. At s equals 0 is 0, and the derivative of f, the first derivative with respect to s at s equals 0 is uvp 1, determines this generating function f uniquely. And this function can be given by an explicit formula. The exponential of f is the exponential of s times u plus v times L1 plus W1 applied to the exponential of u v p1. In particular, this equation implies that f is a solution to the KP hierarchy. That's because both L1 and W1 belong to the Lie algebra GL hat infinity, exactly like for the Hurwitz numbers generating function. Okay, so let me say a few words how to prove this theorem. And the proof is really simple. And it uses the coloring. So the idea of the proof is quite simple. The proof is bijective, and just assume we have a red edge in the belly graph. So the order of edges incident to its endpoints are like this. And we can delete this edge and glue the half edges of the corresponding color together. So we make a surgery on the graph and get a graph with 2 vertices less. Well, outside of this region, the both graphs looks the same, but this graph has 2 vertices less, one white and one black. So what can happen under such an operation? First, we notice that there are brown-green cycles. They correspond to the, they describe the ramification and infinity, and their length is as just these numbers d mi's. So what can happen is the following. Either we have a one cycle like this, then deleting this edge splits it into 2, or we have 2 different cycles like this, and then deleting this edge joins these 2 cycles into 1. This combinatorial situation is described by the 2 terms of the operator W1. In one case, it's the first order operator when you get 2 cycles out of 1. And when you get 1 cycle out of 2, that's the second order part of it. That's the part responsible for it. What concerns L1, it describes the following situation. There may be a double edge, like this. Oops. And when we delete the red edge, we also delete the brown edge, and we get just a green edge out of that. And well, that is described by L1. There are 2 parameters by L1, U and V, depending on whether the second edge in the double edge is brown or green. So that's how it goes. And well, this differential equation is just a way of writing down these simple combinatorial operations on graphs. So the proof is really simple and bijective, so there is nothing there. The only thing is just to carefully count the number of possibilities and to rewrite the corresponding recursions as differential equations. So one of the applications of this theorem is the count of the sons of degree D and genus G. So let it be the number of the sons and let's write the corresponding generating function. Let's call it G. It depends on 2 variables, x and y. And that's just the sum over all the sons of genus G and degree D. G dg x to the d and y to the 2 minus 2g. Let's write it this way. And then this generating function is just a specialization over more general generating function that's written here. So let me write the explicit formula. And this is just, that's easy to see, that's f evaluated at s equal to x to y inverse, and all other variables are equal to y. And so on. So in particular, this theorem gives an algorithm for computing these numbers. These numbers are actually were considered first around 1975. by a combinatorialist. His name is Walsh. He formulated the problem of computing the so-called hypermaps on D darts. Combinatorially, this is the same problem as the enumeration of Grothendieck dessins. What are hypermaps? There are several definitions possible, but the simplest one is like this. You consider D darts like this. We can think of them as segments from 0 to 1. There are D of them. And they are numbered by the numbers from 1 to D. And there are two permutations. Let's call them tau and sigma in ST. The first one tells how to glue the left endpoints, and the second one tells how to glue the right endpoints. For instance, let's take D equal 4 and two permutations, like say, I don't know, 1, 3, 2, 4. That's tau, and sigma is 3, 4, 1, 2. So we have to write them as product of cycles, and to each cycle we associate a vertex. We identify the corresponding endpoints to get a graph that is called a hypermap. So that was not good to write in this notation. Okay, so let's do that like this. So that's the product of two cycles, and that's the product of two cycles of length 2. Then these three are one vertex. And there is one more. And okay, the first one is glued to the third one, and this one to that one. So that's the hypermap that corresponds to these two permutations. And it's easy to see that that's the same as the question of, well, that's the same as the enumeration of the covering with three critical values, because they are also described by two arbitrary permutations and in SD. So Walsh himself was able to write in a closed formula for the numbers GD0 in genus 0, and somewhat later the case GD1 was also considered. There was also written an explicit formula for that case, but little was known about these numbers in general. They were computed for G equal 2 and 3, and D not greater than 12. That was all that was known about these numbers, but say this formula and the algorithm describing this theorem, they allow to compute these numbers pretty fast, and well, they give the same numbers, of course. So, well, I would like to stop here because, yeah, I think I gave an example that is that fits into the picture of Hurwitz numbers, not entirely, but at least partially. Maybe the most interesting part concerning the topological recursion is still open, but at least it enjoys the paths related to the KP hierarchy. So thank you for your attention. That's all.
Questions?
Yes.
So can you consider a situation such that that graph includes a edge with 4 legs or something? So,
sorry?
Edge with 4 legs, and that is a edge, a trivalent edge, but can we replace?
No, the vertices are 3-valent.
Yeah, my motivation is that, okay, so can you include a generalized differential operator which includes 4?
Four critical values. That's what you mean?
Yeah.
No. That's a much more difficult problem.
Yeah, because L1, W1 has some natural meaning in the sense of the conformality theory or something. Because yeah, L1 is associated with Virasoro algebra, and W1 is so generalized and so-called double algebra or something. And it's natural to generalize a much higher order differential equation. So
yeah, but that's an open question. I don't know of any examples of generating functions that satisfy the evolution equations with W bigger than 2 in absolute value. There are examples for W 2 and minus 2 as well. These appear in the polygon gluing counting problems. Yeah, but nothing is known for higher indices of these operators W.
Equations of KP hierarchy, can you give to some of them some combinatorial meaning?
Sorry, what?
Well, you said that this is a solution to KP hierarchy.
Yes.
So there are infinite number of equations.
Yes, that's true.
Some of these equations, perhaps they have some combinatorial meaning also.
Well, no, probably, but I don't know. These KP equations, they're sort of useless because there are lots of solutions to KP hierarchy, and in itself it doesn't tell much about the generating function. But say, so here, this is a question about counting 2 bicolored triangulations. And if you just want to consider simply triangulations, then the KP hierarchy does help. There is a paper by Goulden and Jackson where they enumerate ordinary triangulations of genus G surfaces into, say, n triangles. And this is done by using, well, this an argument that involves the KP hierarchy. So though they prove that the generating function satisfies the KP equations is different from that one. They don't make use of the evolution equation. They don't know this part, this theorem they don't know. But for ordinary triangulation, it does work. For bicolored triangulations, it's not clear.
How would that help understanding the Galois group Q bar over Q?
Well, as I said, it doesn't help much. There are more questions than answers. There is the so-called Grothendieck-Teichmüller group that contains, that acts naturally on dessins, and that can be described in a simple way. And it contains the absolute Galois group. But it's not known whether they coincide or not. This Grothendieck-Teichmüller group was introduced by Drinfeld some time ago in his work on quantum groups, actually. It appeared there. And that's an automorphism group of the profinite completion of the fundamental group of the sphere with 3 punctures.